All right, everybody. Thank you for coming back. Sorry, I'm a little bit late today. Um, I just set up the announcement and the email about the exam. But again, if you have conflict or any changes to approved accommodations, please let me know. We will be running the second exam next Thursday, July 15th. Layout is the same, and the way we'll be gating the questions and everything, that's all the same as it was last time. But I will pause here for a second just to see if anybody has any questions about the exam. Okay, so I want to zoom out a little bit, right? We've been talking about heat engines, right? Now these heat engines are really doing what we call thermodynamics, like literally, right? Because they're taking heat and turning into work, right? So that's why it's a heat engine. It takes heat and turns it into work. Now, we've been specifically talking about Rankine cycles, right? So this idea here that, you give a mechanical engineer heat, and what we want to do is boil water, because when we boil water, we can run that vapor through a turbine and generate power. Then we have to condense that liquid, pump it back up to pressure, boil it again to get back to the turbine so we can keep generating power. And this kind of runs around and around and around. And these Rankine cycles are actually pretty important here in the US and presumably across the world, right? Where they still make up approximately 45% of the power that we generate, at least in 2019. What's happened since I started teaching this class is that the reliance on Rankine cycles has come down a little bit in favor of natural gas power plants. And we'll talk a little bit about those too when we start looking at different cycles. But there are some advantages to natural gas power plants, which are sort of on the rise here in the US. So one of the things that we'll do whenever we talk about these different cycles is we'll think like, how do we characterize the system? That's kind of one of our big questions. How do we see how well is the system doing, right? So the way that we do that for heat engines is we talk about thermal efficiencies. Now, all of these characterization parameters are going to be the energy benefit divided by the energy cost. But in a heat engine, like a Rankine cycle, the energy benefit is going to be what's the net power that we produce. And the energy cost is going to be what's the heat that we have to put in, right? So basically, this thermal efficiency is asking, if we take all that heat that we put in, right, how much of it can we actually turn into work? Because remember, Kelvin and Planck said we have to reject some heat, and any heat that we reject from the system isn't turned into work, right? Because that's the first law telling us that energy can't be created or destroyed. We can compare the actual thermal efficiency that we get to the best possible thermal efficiency we could have, right? The Carnot efficiency, right? If I take T hot minus T cold over T hot, or 1 minus T cold over T hot. Remember, at least in the denominator here, and if you turn this into 1 minus T cold over T hot, it's not always temperature differences, right? And any time in an equation you don't have a temperature difference, that means you have to use absolute temperatures, right? And sometimes people will say to me, Dr. Scherzer, you say that every single time you talk about one of these equations, right? And I say, yes. And still, there will be people on the exam that we have next Thursday, at least if our sample size was big enough, that would make that mistake, right? So we have a smaller number of people writing this exam than would be if we were in the fall or the spring. So my goal is that everybody gets perfect, right? And one of the things that you can do to get perfect, right, is use absolute temperatures when you're talking about Carnot efficiencies, or in any equation where you don't have a temperature difference, right? That's really important. You get a very different answer here, right? Let's say your hot temperature, it would be, I guess, a pretty cold cycle. But if your hot temperature was 0 degrees Celsius, right, that doesn't mean that your Carnot efficiency is infinity, right? Because that'd be 273, right? Your cold temperature would have to be really cold too. So it's kind of, I don't know, it's not the greatest example, except that it shows that numerically you get a very different answer if you're using absolute temperatures or relative temperatures. So what we said, right? When we do these Rankine cycles, we're going to have to look at first law analyses on each of the individual components. And the nice thing is, so far, when we put these things together, right, in this 4-component cycle that we know, that's what we're going to test on the exam, right? So everything is one inlet, one outlet, and steady state for what we know so far, right? So in that case, you know, if everything is at steady state, everything is one inlet, one outlet, we neglect kinetic and potential energy everywhere. And then we have to choose. We look at each component, right? So for the turbines and the pumps, we'll say, oh, those things are adiabatic, right? They're simple systems unless we know otherwise about some kind of heat loss or something. And we'll assume that there's no heat loss, right? So we're just solving for power. In the boiler, it's kind of the opposite. We look in the boiler and we say, well, there's no fan blades in there. Nothing that's producing or consuming power. So we're going to say that it's passive, doesn't have this power term, and we're just solving for Q dot. We'll also assume that in all the lines that connect the different components, and as the fluid is moving through the condenser and the boiler or the steam generator, then we're going to assume that those things have no friction and that there's no heat loss to the system. Right? And if we do that, we can get these equations, at least for the 4-component system that we know. And if the states are labeled in the same way they usually are. One way that I could, I guess, pretty easily tell if you're just memorizing these equations and writing them down, or if you understand where these equations come from, is I could just change the numbering of the states, right? So if I move the, all the state numbers once counterclockwise, then the turbine power would still be m dot times h in minus h out, but it wouldn't be m dot times h1 minus h2 anymore, right? So it's important to know where these equations come from. And as always, my advice to you is going to be start with the base level of the equation, just like I did here, right? And cross out all the things. You don't even have to write down the equation for all the components. You can do it just like I've done here. You write it down once and you say, oh, I'm going to make, this again, I like colored pencils, right? You can say, in Canada, we call them pencil crayons. I don't know if that's a thing here in the US, but I used to say that. This is the great thing about teaching online, right? Is that, if I drop a little Canadianism or something, I can't see all the puzzled looks looking back at me, right? Like if I'm talking about Kraft dinner instead of macaroni and cheese or something, right? Right. So if I have colored pencils, right, or pencil crayons in, sometimes I forget where I was, right? So if I have pencil crayons in my exam, then I can say like, oh, just like I've done here, the assumptions that are in red, I'm making those for all the components, right? The assumptions in blue, those ones are just going to be for the boiler, right? And the assumptions in orange here, those ones are going to be for turbines and pumps and anything else that produces work, right? So if we do that, we get these expressions, right? The turbine and the pump is going to be m dot times h in minus h out, but the turbine power is positive and the pump power is negative. I just add those two things together and I get the right answer. For the condenser, what I do is it's m dot times h out minus h in, at least if I can make all the assumptions that I talked about before, right? And the boiler heat transfer is positive and the boiler heat transfer is negative. Or in the condenser heat transfer is negative because there we're losing heat. Right, now we did this, right? And we did a Rankine cycle a couple classes ago, right? And we found here that our thermal efficiency was 28.4, right? Which seems kind of depressingly low. So it's basically like not even a third of the heat that we put into the system was used to make power, right? So, and we pay for that heat, not just economically, right? But environmentally too, right? So if we're burning coal to make this heat, we'd like to make it so that we're minimizing our emissions, right? Or at least reducing them, right? And here, I feel like 28.4%, that's pretty low, right? But I can't just compare that to 100%. I have to compare that to the Carnot efficiency, right? So we did that in a different version or a different part of the class, I think, maybe even just the same like, part D or something of the problem, right? That's something you could be asked to do on the exam, right? So here, the actual efficiency that we got was 28.4, but the Carnot efficiency was 55.3. So even though I can never get this efficiency up to 100%, the highest I can get is 55.3, but I'm only at like half of that. So how do I get it better, right? That's going to be the focus of the class today, is how do we take these Rankine cycles and make them better? How do we improve the thermal efficiency so we're either getting the same amount of power with fewer emissions, or maybe we're keeping the emissions the same but producing more power? Either one of those things is really good, right? So that's what we're going to try to do. Right? So why do we want to improve thermal efficiency? Right? Now, this is kind of our role of engineers, right? Because as engineers, I'd like to think that there's a social responsibility involved with being an engineer, right? Now, this is, if you do your iron ring ceremony here in the US, in Canada, we call it a Kipling ceremony. So it's done a little bit differently here in the US, but it's kind of modeled after that same system that we have in Canada. And it really talks about, the important responsibilities that we have as engineers when we're, when we're looking at, we're like the representatives for the society in a company, right? So we sort of take that, societal role and translate it into business speak, sort of, right? So one of the arguments we can make for why thermal efficiency is important, right, is because it means we're going to save a bunch of money, right? So this is, as engineers, you got to know how to talk to your bosses, right, or to your, to the business people that are running the company that you're working for, right? And the numbers that they pay the most attention to are probably going to be the numbers that have dollar signs in front of them, right? So if I'm going to be running a coal power plant and I say, oh, we can reduce the amount of heat that we're putting in by 1%, right? Then what that means is we have to buy a lot less coal, right? So our costs go down, right? So then our profit goes up, right? Because profit is revenue minus cost, right? Or maybe our costs stay the same, but we're going to produce more power, which means that our revenue goes up. So again, profit, which is revenue minus cost, goes up. Right? So we have to be able to speak that language. And honestly, it's really important, because if we want to work for a company that's doing things that we think are good, for that company to survive, it needs to be generating profit. Right? So we do have to think about the economic implications of the things that we want to do. Right? So a lot of the things that we'll talk about here, it's tough. And, maybe as you go into contemporary issues, which I've taught in the past, you'll learn a little bit about economics too. I would suggest, and maybe this is, everybody thinks the path that they took ends up being a good path if they got to where they wanted to get to. But both my wife and I, we met when we were undergraduates. She's a mechanical engineer as well, but we took this double major in engineering and commerce or business, right? So basically all of my electives were in business related courses. Right, so I ended up with a double major, right? So a major in business and then in engineering, right? And then my wife took that and did an MBA in a year, and I think it's a super powerful combination, because you kind of get the analytical and technical expertise of an engineer with the kind of ability to, translate all that information into business speak, right? And deal with people again. So a lot of my friends went through this same program. And, they did more technical engineering jobs in maybe the first 5 years or so after they graduated. But, as my gray hair attests, maybe I've been graduated for a little while now. And I think most of my friends are in business now too. So they're still engineers, but they're maybe managing a technical team. So it's, it's an important thing, right? But, the other thing that we got to look out for, right? The other argument we can make for improving thermal efficiency is that, Earth's a pretty good place to live, right? In fact, there's nowhere else in the universe I'd rather live than on Earth, right? So, we do have a responsibility, right, as sort of drivers of technological change to try our best to, to minimize the environmental impact of the things that we're doing, right? So the other argument here is that as we're improving thermal efficiency, right, we're reducing our environmental impact, right, our environmental footprint. So there's two different ways to look at this, and they're both good, right? This is one of those things that's a win-win situation, right? So this is the kind of argument that I think is, good to be able to make, especially if you can justify the profit part, right? Because then, my experience isn't vast, right? But in my experience, it seems to me that the environmental changes that tend to resonate, that tend to be successful with people, are the ones that end up also having environmental benefit, right? So, if you can improve the insulation in your house and that reduces your heating bill by enough to justify the initial cost, then people do that kind of a thing, right? So one of the nice things that I've been saying, right, is that, sometimes we'll look at different, we'll make different models, right? And as we make these models of the universe, we make assumptions. And as we make assumptions, we're coming more and more away from reality and towards this cartoon level of an understanding of the universe, right? And, this Carnot efficiency equation is one of these models, right? And it's very simple because we made a ton of assumptions. We know that this equation, we can't actually get an ideal engine, right? But the nice thing is we get this very simple mathematical equation. And from this, we can see two ways where we should be able to improve the efficiency of the system, right? So it's a simple model. It gives us a simple equation. But from that simple equation, we can use this and say, well, we want to get closer to 1, right? That's 100% efficiency. And really, I only have 2 levers here. If I look at this equation, 2 variables I can change to get closer to 1, right? So there's 2 ways that I can do this. I want to minimize this negative term, right? And if you look at this, you can probably tell me what those 2 things are, right? So the first thing is I can increase the hot temperature of my cycle. If I do that, right, then this fraction over here gets smaller because the denominator gets bigger. If I could increase this T hot to infinity, then my Carnot efficiency would be 1 or 100%. The other thing that this equation suggests that I could do to at least improve the efficiency of the ideal system, but maybe that puts me on the right track. The other thing I could do here is decrease T cold. If my T cold was absolute 0, then I'd have 1 minus 0 over who cares what T hot is, because it's still 0, and that would be 100%. Now, that's not practically possible because you'd probably be spending more resources to, get to that absolute 0 temperature, which we can't actually get to. Although my understanding, it's not my area of research, but I think we're getting very close to absolute 0, but I don't think we've ever really hit it, right? But those are the 2 things that we can do, right? So here, the first thing that I'm going to look at is how do we increase T hot? So maybe the very first steam engines, right, would go through and they'd boil water, and maybe they'd get to the point where they have saturated vapor, right? So how do I get my temperature higher? Right here on this TS diagram, what I want to do is increase my hot temperature. That's the temperature my heat is coming from, because as I increase this place, remember what I called the 0th law of thermodynamics, or maybe what my old professor called the 0th law of thermodynamics, is this idea that heat only goes from hot places to cold places. So in order to get my temperature going into my turbine hotter, I have to be making something hotter than I'm, where my heat source is, in order to maximize that temperature, right? So one thing I can do is I can just keep adding heat. If I get a fuel that burns hotter, right, then maybe I can make more heat. As I make more heat, I get up into the superheated vapor region if I'm not changing the pressure, right? And then I go down through the turbine, and then I have to condense a little bit more. So if I do this, on the surface, you might say, well, that's bad because we're using more heat, right? And that means we're burning more coal potentially, or maybe we have a different fuel source that, that generates a higher temperature. But I am increasing the work out, right? So really, when we think about thermal efficiency as net work divided by heat in, really what we want to be doing is increasing the net work faster than we increase the heat in, right? And that's essentially what we're doing when we superheat the fluid, right? So when we get the inlet of our turbine up into this superheated region, then we increase the thermal efficiency. What's another way that we can increase the temperature, right? So we can go supercritical, right? And this sounds like, I don't know, it sounds maybe more exciting than it is, right? But remember, the critical temperature is or maybe the line for the critical pressure would be this constant pressure line that would come and just kiss the top of the vapor dome, right? And the critical temperature associated with that would be a horizontal line that, again, is just kissing the top of the vapor dome here, right? But if we can push that, if we can get to a higher pressure and add heat, right, then we can skip the vapor dome entirely, right? And we end up here, right? So this would be a supercritical Rankine cycle, right? So, we do increase the pump work, but we know in Rankine cycles, pump work's not that important. That's kind of the reason that we condense the fluid, is it takes very little power to increase the pressure of a liquid, at least relative to the power we're going to end up generating because of the turbine, right? We do need to increase the heat in, but we increase the turbine power, right, such that the net work is increasing faster than the heat transfer rate in. So again, using a supercritical Rankine cycle is another way that we can increase the hot temperature and increase our thermal efficiency. Now, why don't we just increase the temperature like to infinity, right? And beyond, right? As they'd say in Toy Story, right? Buzz Lightyear, right? I was trying to remember the name. But there's practical limitations. There's always practical limitations. That's kind of our job as engineers, right? Is to figure out first physically what, changing different knobs or levers is going to do, right? And then try to work within the real limitations of an actual process to make it work better. Oftentimes, as I've said before, without having a perfect understanding of how the universe or the physical behavior of our system works, right? So we got to try to, make things better without that perfect understanding, right? So we see that increasing T hot would be good, right? But there's two things that really limit this, right? The first we've already talked about, or I guess it's the second on this list, is we need a fuel that burns at a higher temperature, right? So we can only transfer heat into our working fluid from something that's hotter than our working fluid is. Right. So we need to, maybe we're working with chemical engineers and they're, making better fuels that burn hotter, right? Like my understanding is that jet fuel burns hotter than gasoline, right? Even though they ultimately, my understanding is they come from the same place. Now, a chemical engineer probably is going to know a lot more about that than me, but that's kind of my understanding, right? But the other thing that could happen is that we're dealing with the material properties, right? So it's not so good if I can increase the temperature of my cycle so high that my turbine melts. Like, that's not great for the cycle, right? So, we're also working not only with chemical engineers who are making, better and better fuels, we're working with materials engineers, which is a branch of mechanical engineering, who are making better and better steels that can withstand higher and higher temperatures. Right? And then, when you're dealing with those different steels, then you got to work with manufacturing people, right? Because maybe that steel is harder to work with, harder to get the right kind of shape or profile on that turbine blade, which is going to potentially improve your efficiency as well, right? So, there's different limitations, but generally, if we can increase T hot, we can see that we can improve our thermal efficiency. So what's something else we can do? Right? We can reduce T cold, right? Because that thermal efficiency, at least for the Carnot version, right, is 1 minus T cold over T hot. So if I can reduce the cold temperature, or the temperature that I'm rejecting heat to, if I can decrease that temperature, then I can improve my thermal efficiency. So oftentimes in these Rankine cycles, we'll actually drop the pressure quite low in the condenser, often much less than atmospheric pressure. Right? So now my turbine line comes down over here and then across, right? And then we're rejecting heat to some, thermal or heat sink, right? So we talked about this, right? How you can potentially do this, rejecting heat to lake water that you're pulling out of a large body of water, something like Lake Ontario. So you're not, it has to be a reservoir. We have this term in thermal fluids called a reservoir. So that means, the lake is really big. So even though I'm dumping heat into it, I'm not actually changing the average temperature of the lake because it's so big. Its thermal mass is so large, right? So you couldn't necessarily do this on a small lake, but Lake Ontario is pretty big, right? We're quite lucky, quite blessed to be so close to so much fresh water here in upstate New York, or where I used to be in southwestern Ontario. Right. So again, if we do this, we're doing things like increasing the pump power, right? But we've seen that pump power is not that big. And again, what's happening is we're increasing the power faster than we're increasing the heat transfer that goes in, right? And that improves our thermal efficiency. So those are the two things that we get from looking at our thermal efficiency equation, right? If we're using the Carnot equation, right? But the normal equation is going to be net power divided by heat transfer in, right? So, and I've been going on and on and on and on. Actually, I'm going on about how I'm going on about the Lego thing, which I don't know, maybe it's getting too much. But, we've been talking about Lego, right? And how these processes are like Lego blocks and we're putting them together in cool ways, right? And what we're going to test on the second exam, right, is kind of a simplistic version of what a Rankine cycle might be, right? So it's kind of like the Duplo version of what Rankine cycles are, right? But by the time we're done next week, right, the stuff that we'll be looking at on the final exam gets away from just using 4 components, right? And what happens is we increase complexity, right? So we become these kind of master builders that start to use all these different techniques, improving the complexity or increasing the complexity of the system to improve the thermal efficiency. And we're going to talk about the first strategy for doing that today, right? So we're going to talk about what we call a reheat, right? So if we look at the expression for thermal efficiency, not ideal thermal efficiency, but just thermal efficiency, it's net power divided by the heat transfer rate in, right? So again, I can look at this equation and see, well, if I could increase my net power and not increase my heat transfer in, then I would improve thermal efficiency, right? Or if I could decrease the amount of heat that I put in and keep the net power the same, then that would also increase thermal efficiency, right? So it's true that both the, strategies for increasing the complexity, they're both changing power and heat transfer, and they're both, increasing the power more than they're increasing the heat transfer rate, right? So the thermal efficiency goes up, right? But I like to think about this first strategy, which we'll call reheat, more as increasing the net power, right? So it looks at this Rankine cycle and it says, well, if one turbine is good, maybe two turbines are better, right? So let's try it out. So what we do here, right, is we've increased the complexity by adding more processes. So there's 2 processes that we've added here, right? One is a second turbine, right? So we have what's called a high pressure turbine, right? Because, the fluid comes into this turbine at high pressure. And what happens in the turbine is the pressure goes down, right? As we're taking the enthalpy from the fluid and turning it into mechanical work, right? Or power, right? And then we're going to go through this second heating phase. That's the other thing that we're going to add, right? And then we go through this low pressure turbine, right? So we won't get as much power out of the second turbine, but we go back into the boiler and we produce more power than we otherwise would have, right? Now, it does come at the cost of adding more heat to the system, but in a way, or at least the way that I think about it here, is like we've already got this boiler over here. It's already at some very high temperature. Let's just run the lines back through here, right? So it means that we're going to be, there's more heat that's going into the fluid, right? But, I imagine anyway that the physical complexity here. It's not like we have to build a whole new boiler, right? It's probably not a trivial thing to put more, tubing in here and better heat exchanger or whatever, right? But it's not like the boiler's already there, right? So in between these two turbines, if we didn't go into another boiler, it didn't go back into the boiler, it wouldn't really be too much different, right? But because we're reheating the fluid, we're adding more enthalpy to the fluid from state 2 to state 3, which means that there's more enthalpy to take out here in my second turbine. Now the rest of the cycle looks the same, right? It's a condenser and then a pump and then a steam generator or a boiler, right? So I think of this as adding more work because we put in another turbine, but we're also increasing the heat that we put in. But again, because the thermal efficiency goes up, it means we're increasing the power more than we're increasing the heat transfer rate. All right, so here we're going to ask the question, is the thermal efficiency better? Or maybe, how can I find the thermal efficiency, right? I don't think it's a big spoiler here to say that we wouldn't be teaching this to you if it didn't improve the thermal efficiency, right? So, at the risk of spoiling the punchline here, yeah, efficiency gets better, right? So the first thing I want to do is talk about the TS diagram. So in the 4-component Rankine cycle that we know that we'll test you on in a week's time, right, is, it's got 2 pressures. It's got a high pressure and a low pressure, right, and 1 turbine, right? So here we take that turbine away and we're going to put 2 turbines, right? But that means we need some intermediate pressure, a pressure that's in between the high and the low pressure that we see in the system, right? And that first turbine, the high pressure turbine, goes from the high pressure to the intermediate pressure, right? So I'm showing that as coming out something like a saturated vapor. Then we add, so that's the first turbine, right? The high pressure turbine. What happens next is we go back into that other heater, right? So we do reheat, right? And because we're adding more heat, right, then we stay at that same intermediate pressure. We assume there's no pressure losses in the system here while we're adding heat, right? But the temperature goes up, right? So it looks like this on my TS diagram. And then I go through the second turbine, right? And that second turbine produces me some more power. And then I have a little more condensing to do, right? Which means that I'm rejecting more heat, right? And Kelvin and Planck say, yeah, of course you have to reject heat, right? So when I do this, I do increase the heat transfer in, which on its own looks like maybe that wouldn't be that good. But because I generate more power, like the increase in the power is bigger than the increase in the heat transfer rate. So what happens is we get a better thermal efficiency. The textbook talks about this as increasing the average temperature of heat generation too. So that's another way that you can see that maybe your thermal efficiency is increasing. So how do we go about analyzing a cycle like this, right? So the first thing that you might see on a final exam that has reheat in it is you'd have to draw a TS diagram like this, right? But then the next thing is, well, how do I characterize the system, right? So again, the benefits of reheat is that we're increasing this average temperature of heat addition, right? We get better steam quality as we're going through, right? So we're not going through the turbine here from 2 to 4 prime, right? That's how we used to do it, right? But now we're going to go through this second turbine over here and we're cutting through the vapor dome less, right? So that generally means our turbines are doing better, right? So they'll produce more power. So thermal efficiency is the same equation that it always is if you look at the base level, which I'm always going to encourage you to do. The definition of thermal efficiency of all these characterization parameters is benefit over cost. But the benefit of thermal efficiency is net power, and the cost is heat transfer rate in. Now it's a little more complicated because there's more processes to talk about. So we got to pick the right process, right? So first we'll look where in this system is power important, right? So I have turbine 1, I have turbine 2, and I have a pump, right? So before, in the 4-component cycle, I only had a turbine and a pump. Now I have 2 turbines and a pump, but that's okay. My first law analysis is ultimately going to be about the same, right? I'm going to say, oh, it's at steady state. These things, they have 1 inlet and 1 outlet. I'm going to neglect kinetic and potential energy, and I'm going to say that they're adiabatic. And if I do all of those things, right, then I'm going to get the equations that I'm used to, right? But I guess even before I do that, I can break down net power, which used to only be, if I was going from the first law, turbine power plus pump power, recognizing that the turbine power is positive and the pump power is negative, right? That's why I got the color coding here. But now it's more like, oh, the sum of all the turbine powers plus the sum of all the pump powers, right? Even though there's still only one pump, right? But there's a general way that we can look at that and say, add up all the turbine and pump powers, right? Recognizing, again, that we're adding negative numbers when we're talking about the pumps. For the heat transfer rate in, this is, it's kind of silly because this thing is called reheat. But for me, if I'm going to make a mistake, I usually remember that there's two turbines to analyze. But sometimes if I'm doing these problems quickly, I'll forget that there's two places where I'm adding heat. So I got to remind myself, hey, Mike, this thing's called a reheat cycle. That means that there's two times we're adding heat, right? So here, there's two terms in the denominator as well. They're both positive because they're both about heat addition. And we're looking at adding heat in the boiler the first time and the second time, or sometimes I'll say Q dot B for the first one is boiler and Q dot RH, reheat, for the second heat transfer phase in here. So if I write out my thermal efficiency, I can say, okay, it's going to be the power from turbine 1, positive, plus the power of turbine 2, positive, plus the power of the pump, negative, divided by the heat transfer in the two places where I'm adding heat, right? Or generally for any cycle, right, where we're talking about a heat engine, at least if it's an open cycle, then, or a series of open systems, right? Then I can say it's the thermal efficiency will be the sum of the turbine powers, which are positive, plus the sum of the pump powers, which are negative, divided by the sum of all those places where I'm adding heat to the system, right? That's the general open, system version of thermal efficiency. Right now, I'm going to look at each one of these components, just like I did with the 4-component cycle. I'm going to say, oh, they're all at steady state. In this case, they're still all one inlet and one outlet. A little bit of foreshadow there. We're going to neglect kinetic and potential energy changes. And then I'm going to look at the components and I'm going to say, well, for the turbines and the pumps, I'm going to call them adiabatic, isolate for W dot. And for the heat transfer places, right? So like the boiler and the reheat, I'm going to say that they're passive and isolate for Q dot, right? Again, I'm going to assume no frictional losses anywhere, and I'm going to neglect heat losses in the, lines that connect our different components. If I do that, I'm left with the equations that I'm used to, right? The turbine powers are m dot times H in minus H out. They're positive. The pump powers are going to be m dot times H in minus H out. They're negative. The condenser, which we didn't really talk about too much here, but if I'm just looking for how much heat is rejected, I can get m dot times H out minus H in. That's negative because heat's going out. And if I look at the boiler, the place where I'm adding heat, then that's going to be m dot times H out minus H in, right? That's in the different places where I'm adding heat. So the thing is, right here, I've just generically said H in minus H out, because then this works for any of the turbines and any of the pumps, right? But then what I have to do, right? So first I got to think, okay, what's the fluid, right? The fluid is water. That means we're going to go back and forth across the vapor dome. So I got to fix the states. I got to remember how to fix those states, right? But then I got to think, well, where are the actual components, right? So it matters what this diagram looks like, right? Or maybe this diagram, right? So for my first turbine, my inlet state is state 1, and my outlet state is state 2. So m dot times H1 minus H2. For my second turbine, my inlet state is state 3, and my outlet state is state 4, right? So, this should be 3 to 4. Sorry about that. Then my condenser, right? If I was looking for how much heat was getting rejected from this condenser, this would be m dot times H out, which is H5, minus H4, which is H in. Right? So we expect that to be negative because we're rejecting heat, right? The turbine powers were positive. The pump, there's only one pump in this system. It's it's going to be m dot times h in, that's h5, minus h out, h6, right? And pump powers are supposed to be negative. The boilers, and again, if I'm going to mess one up, it's that I forget to put the second boiler in, right? Or the reheat phase. This is m dot h out minus h in, or h1 minus h6. And this other one is m dot times h out, h3, minus h in, h2. Right? And so that's how I go from this general process to specifically what's going on in this cycle. And this is what I want us to think about when we're doing all of these. So from here on out, it's all cycle analysis, right? I want you to think about all of these cycle analysis problems as the same problem, right? So we're going to look at the cycle. We're going to say, how do I characterize the cycle? What's the energy benefit? What's the energy cost, right? And then I'm going to say, okay, is it a series of open system processes or closed system processes, right? And then I'm going to use the first law to analyze each one of those processes, right? Then I'm going to get symbolic solutions for all of the processes in the system, right? So it's going to be, equations like this. They're m dot times delta H, right? Or maybe if it's closed systems, it'll be m times delta U, right? And then I got to ask myself, well, what's the fluid, right? Because if the fluid is water, I got to fix the state by looking at, what's the phase, right? So is it two-phase? Is it liquid? Is it vapor, right? And then if it's air or some other ideal gas, then I got to say, okay, is it constant specific heat or variable specific heat? So that's kind of there's two ways to go about doing thermodynamics, right? The first is to memorize everything, right? Now, it might just be because I don't think I'm all that good at memorizing things. There's a lot if you try to memorize things in this class, right? So that's why what I'm trying to teach you is what's the roadmap, right? What are the principles that you need to solve problems like this? Because then it doesn't matter, right? I can give you on an exam, and I've done this before, ones that have 4 turbines and they have reheat, right? And then they have what we'll talk about next class or maybe the class after that, is regeneration, some other increased complexity thing. And maybe they have 2 reheat stages and 2 regenerations, right? And it's super complicated. And the first thing you might think when you look at that is like, oh my, how am I ever going to answer this problem? It's so complicated, right? And then hopefully there's a little Dr. Schertzer on your shoulder saying, don't worry about it, right? You look at what's the general equation for my thermal efficiency, right? It's going to be the sum of the turbine powers plus the sum of the pump powers, which are negative, right? And then I got to divide that by the sum of all the places that I add heat, right? So I look for all the places where I'm adding or consuming power, and I look for all the places where I'm adding heat, and I do a first law analysis. And probably I'm going to get a whole lot of m dot times h in minus h outs for powers, and a whole lot of m dot times h out minus h in for heat transfer rates. And then I'm going to say, oh yeah, what's the fluid, right? Because once I know what the fluid is, then I can fix the states and I can get numerical answers, right? So you won't get this on exam 2, because exam 2, if there's a Rankine cycle, we only covered for exam 2 the 4-component Rankine cycle. So that's what you'll see on exam 2. But when you get to the final, things are going to get complicated, right? We got lots of different cycles, and they'll have lots of different potential complexities. But try right from the beginning here to think about this as they're all really kind of the same as this 4-component Rankine cycle. I just got to break it down, right? I just got to take my time, right? Like Dora says, I got to stop and think, follow the process, and you'll get to a good answer. Even if it's not exactly the right answer, you'll certainly have demonstrated that you understand the process. And that's the most important thing, I think, certainly in engineering, probably in just life in general, is, try to follow a good process and you'll get good results more often than not, right? And I think that's the best that we can hope for. I am done for today, but I'm happy to stick around if people have questions. And I will be around in office hours at 2 o'clock.